everyone. My name is Georgiana Kong, and I participated in the SIPTA program at Evonik Birmingham Laboratories, and I did my presentation on the spatiotemporal effects of atmospheric plasma treatment on biodegradable substrates. So I'm going to start off with some background, just saying why we did this study and why it's important. And so starting off with talking about degradable polymer biomaterials, these are the materials that we used for our substrates in this study. And they are expanding in scope and expanding in use for medical applications currently. This is especially because in clinical applications, you don't have to go in for another surgery or procedure to remove these devices, and they usually will just dissolve or resorb into the body. And there are degradable polymer biomaterials that are made of both natural or synthetic polymers, so they both have their own pros and cons. The natural polymers, these are more representative of biological conditions. However, they are lower in strength and consistency since they are natural and not man-made in a lab. And some examples of these natural polymers include chitosan, collagen, gelatin, and elastin. And then on the other hand, the synthetic polymers that are used in these degradable biomaterials, these ones have favorable mechanical properties and predictability because they are man-made. However, they often lack in biocompatibility since they are not made of those natural materials that are usually found out in nature. And some examples of these synthetic polymers include polylactic acid, which is PLA, polydioxanone, which is PDO, and polylactic coglycolic acid, which is PLGA. Talking about surface modification of polymer biomaterials, there are two types of high energy irradiation techniques that are used often in labs, and that's UV and plasma treatment. And so both of these techniques alter the surface of the material without affecting the properties of that bulk material. However, UV is a more mild and it doesn't last as long compared to the plasma treatment. And so plasma treatment, it is used to increase the surface energy of that material. It generally adds polar functional groups, but it completely depends upon the type of gas that is being used in the plasma treatment. And it is often used to enhance the hydrophilicity of the material. And for plasma interactions, one major advantage of these interactions is that it is not a line of sight process. And this means that since it is done under a vacuum and there's gas that's being used, it coats the entire surface in a uniform manner compared to other ways such as UV and laser, which it has to be in the direct line of sight of that treatment. And there was a study by Yang et al. That showed on PLA, it actually improved the cell retention and it reduced the amount of waste that occurred due to cell culturing because it allowed those cells to stick more easily into the wells. And next is talking about additive manufacturing, and this is another name for 3D printing. The two methods that I used this past summer were SLS and FFF. So SLS is selective laser sintering, and this is a unique method which fuses powder particles through using a high-powered laser. And this is a more unique method because you can print more complex geometries, and there are supports. The supports that are usually required in 3D printing are not required in this method, and that's because the powder that is in the banks actually acts as the supports for this. And the other method I used was FFF, which is fused filament fabrication. And this is the more common method. This is what you would probably think of whenever you think of 3D printing. And this is when filament is extruded through a heated nozzle. And the filament is coming from a spool compared to SLS, where it comes from a powder. It is less detailed, but it does often have higher durability since the material is solid and it comes out onto the heated bed. And going into the methods for this experiment, talking about the substrates. So the substrates that we used were just cylinders that were 20 millimeters in diameter, 10 millimeters in height, and you can see that CAD rendering to the right. These were an arbitrary shape. They were not important to the results of the study, but we just used this shape because it was compatible with the well plates that we would use for our experiments. It was designed with CAD software, and then we converted it to STL format, which are these triangle formats which you use in the slicer for 3D printing, and then we use the Ultimaker Cura slicer. And then for pore size, we changed the pore size differently for both the samples. So in the FFF, since it is a solid filament, we had to change the infill density of it. So pretty much whenever you 3D print, whenever it goes along the bed, we just changed the size of those triangles that are on the inside of the material. And so we changed it from 25% all the way up to 100%. And then the SLS, since it is a more grainy material and it's from powder that's being sintered together, it is a porous material. And so we changed the laser power and speed to alter the amount of energy that got transmitted to the material. And then for the plasma treatment, we use the AutoGlow 200 machine by Glow Research, which you can see in figure 2. And for our gas, you can often use many different types of gases, such as oxygen or nitrogen, but we used ambient air, so it's kind of a combination of all of that. And we used a constant power of 25 watts, but we changed the amount of time for treatment. So we started at our control of 0 minutes, then we did 1, 5, and 10 minutes. And then for our characterization, we did peptide adhesion studies. We also did SEM, which is scanning electron microscopy, and contact angle. And then we performed anhydrous staining on our peptides. And for our results, first, I'm going to talk about the SLS results because there was a lot of troubleshooting that had to occur with our powder printing. And so I adjusted the power and the rate in doing all of my trials. And then I found that whenever the energy transfer was too high, we would end up with powder clumps and the layers would end up sticking to the recoater because they were still wet whenever the recoater was coming to swipe a new layer of powder. And this resulted from too high of power, so too much energy being transferred, or too low of rate, so the laser was going too slow and also putting too much energy into the material. And then whenever the energy transfer was too low, it ended up in a powdery finish. And this ended up in the object not being able to adhere to the build plate since there was not enough energy in that material. And this would result from either too low of power, so there was not enough to sinter the powder properly, or too high of rate, so the laser was going too fast to sinter the powder. And then I have a list of all of my trials going on. So on the first one, you can see that I turned the rate down, and so the laser was going super slow, and then it made the powder get really brittle, and it kind of sintered it too much. And then whenever I turned the power up as well, we noticed that same characteristic of the powder just getting really brittle, and it was completely over-sintered. And then whenever I turned the rate up instead, the material was really lightweight, and that was because there was not enough sintering occurring. And then that next to last trial, the rate was turned down and the power was turned down, but it did not end up sticking to the bed for a while. And so that is why you can see those ridges at the bottom. And then it eventually did get to a good temperature and energy getting transferred to it. But in the end, we found that adding a raft and turning the power down, but also turning the rate down completely, had the most successful trial for printing this material. And so in figure 4, it shows the successful SLS print. Again, we found the highest success at a low speed and low power. We think that it's because the low speed allows for enough energy to be transferred to the material. However, the low power as well was needed to enable the precision in sintering, because too high of power would make the material heat up too quickly, and it would make the material become warped. And we also found that a raft increased the likelihood of the object adhering to the build plate because it did have a higher surface area, allowing the material to have a higher chance of staying. And then getting into the plasma treatments, so we did the peptide staining experiments. And so with the FFF, we actually did not observe any peptide staining, and that is because possibly the filament was solid, and so the filament is not porous at all. And so it was presumed to possibly be too non-fouling or too non-porous to have any peptide staining, even though we did have the pores altered as the infill density. It did not show to mount any effect. However, in the SLS, we did see a lot of different results with this. So in the SLS, we kind of had the observation of there was a complete absence of adhesion whenever there was no plasma treatment on it, but there was a presence of peptide adhesion whenever there was plasma treatment on the material. And I'll go into those results a little bit more. And so with the lower density, so we tested it on a low density material and a higher density material, which was made from the SLS. And so in the low density trials, we found that the longer plasma treatment time increased the adhesion of the peptide because it increased the amount of staining that occurred. But there were negligible differences between the two time points of 5 minutes and 10 minutes. So after a certain amount of time, there isn't much more of a change that occurs from a higher time of plasma treatment. And then the higher density trials, it was a little bit different. So we saw the result that a longer plasma treatment time resulted in a deeper color stain, as you can see all the way up to the 10 minutes. However, there was a weird observation that the 10-minute stain, it was concentrated completely in the middle of that surface. And so this was possibly due to the fact that our higher density samples, they were created way earlier in our SLS troubleshooting time, so they might have had inconsistent surface character, and this led to the presumption that the plasma as well as the surface quality would affect the surface character and how the material responds to a treatment. And so I ended up studying that in a little bit more detail. So I just used one of my samples that was completely rough and I compared it to a control, which was more smooth. And that rough object, I also treated it for 1 minute with the same power of plasma, but it ended up with a much greater amount of stain compared to the other plasma trials. And so overall, this led to the conclusion that lower density samples, they had slightly more peptide adhesion because they were a little bit darker in color compared to the higher density samples. And this could be thought to be due to the fact that there was more surface area since they were a little bit more porous. But we also found that the quality of the substrate affects the material performance even at the same amounts of treatment. And then a little bit of an extra data point that we observed was on contact angle. So we did a contact angle measurement on a control, and then we did it on the 1 minute and 10-minute trials as well. And so we found that on the control, there was an average of a 126-degree contact angle, which the material was pretty hydrophobic. But even in the presence of 1 minute all the way up to 10-minute, there was a 0-degree contact angle, meaning that the material became hydrophilic even in the presence of 1 minute of 25 watts plasma treatment all the way up to the 10 minutes. And then upon observing it with our SEM, the scanning electron microscopy, there weren't any visible changes in the roughness of the material, but we did find that there was a little bit of melting occurring at the higher plasma treatments. And then so for my conclusion, I found that the treatment with atmospheric plasma will affect the surface character by adding functional groups based on the gas that change the properties of the material surface. And the atmospheric gas, it increased the hydrophilic character of the polyester print powder. This was observed through higher peptide adhesion, as well as the contact angle completely being diminished to 0 whenever in the presence of plasma treatment. We did find that there were diminishing returns from the plasma as treatment time increased. So from the 5 minute to 10-minute trial, there were not visible differences. And then lastly, we found that the surface quality of the material as well as any treatments affect the character of the material surface. And this concludes my presentation. Thank you all for listening.
Hello, my name is Kelvin Lule. I'm a PhD candidate at the University of Alabama in Huntsville in the Space Science Department, and my advisor is Dr. Gary Zenk. Today I'm going to be presenting my internship project, which I did with Aspect Aerospace from Mobile, Alabama. And the title is going to be Modeling Moving Plasma Disturbance for Ionospheric Forecasting. This is a new topic I'm going to be talking about. So because of that, I had to filter so much information which I couldn't share, since this presentation will probably be a public record. But I also try to do my best to put everything together to try to paint a picture of what we're trying to do. My mentors were Drew Ross, Dr. Spencer Edmond, and Dr. Samuel Ross. I think the two of them are here, so I'm glad you guys are rooting for me today. And then the sponsors, FTPP, Alabama, with Aspect Aerospace. I appreciate the opportunity. So let's get into it. I made a quick outline, which I'll do the introduction, then show a quick space weather parameters, then a little literature review of what we are doing, then the workflow, then I designed a simple flow chart, then plasma cloud, then our short results and the lessons learned during this internship or program. With the introduction, our major objective, we're trying to do like forecasting. So I decided to explain to people a quick review what space weather is. It refers to the conditions in space driven by solar activities, such as solar flares, geomagnetic storms that can impact the satellites, power grids, and communications. This is one of the reasons space weather is a hot topic of research now and industries because there are so many problems we're trying to solve, as well as saving a lot of money in the process if those problems are solved. Again, with my focus in space science, we focus using plasma in doing that. So I also made a quick definition of what plasma is. Plasma is an ionized gas consisting of free electrons and ions, and is the most common state of matter in the universe. Most people don't know this, but most of our universe is literally 99% of plasma as compared to other elements. Then the importance of this, like I said earlier, changes in plasma density and movement can significantly affect space weather, influencing our communication systems. And satellite operations are I'm highlighting this, like the satellite operations, because at aerospace, we are more focused on like dealing with developing a system which has so much to do with satellites and everything. I may not share too deep of what that is, but I'll do my best to, oh, my bad. I'll do my best to, to show what we're really working on in that aspect. Then real-time space weather parameters. I try to show the space weather parameters, which we are going to be dealing with in designing our model or the process. One, we're going to work with solar wind speed, solar wind density, and solar wind magnetic field, Z, which is perpendicular magnetic field. In my department, we focus more on solar wind, but most of the time it's far away from what we are working on or what we worked on with the aspect, which is a great opportunity for me to learn something new and looking at solar wind or solar parameters in a different perspective. And then the geomagnetic indices, also this is going to be used through since we're trying to, for example, predict or forecast the space weather system. So we have to measure the magnetic activity and disturbance. We also have to do the strength of the ring current around the Earth affecting the geomagnetic storms. These also kind of fall into our general research, but as far as our project is concerned, we're focusing more on the ionosphere. So understanding this is going to be a little bit more complicated just as it is here. It doesn't necessarily appear like this because we're dealing with different altitudes. And then the importance of advancing space weather forecasting, a quick review, satellites, for example, prevent communication and navigation disruptions, which protect electronics. We know if we don't be able to predict or space weather and we get a rough magnetic storms or anything, that can, for example, we can take a case study from a few years ago. SpaceX had one of these problems where they underestimated the impacts of space weather, and they ended up losing almost 38 satellites, if I'm not mistaken. Then the power grid, we avoid the voltage instability in transformers because also, as we know, space weather also directly affects the voltage and creates instability into the system, which could critically damage the infrastructure in the power grid. Then aviation, as you move up, for example, the planes, this reduces the risks of radiation exposure on high altitude because the pilots or operators are told when it's safe to fly in certain areas during certain problems. This is also done by people who specify specifically professionals in space weather. Then mitigating costs. Of course, you save billions if you predict, catastrophes before they happen, and we get a chance to do something about it. Then our astronauts for safety protocols in space missions, then the air crews, to mention but a few. Then our workflow, most of it, we started with synthetic data in space weather models, doing so many research, comparing and reading from previously done models to see, because people have done research in the same industry, but we're trying to do something different. So we're creating a plasma model. I didn't give so much details again because I can't really give away everything. Then we did the interpolation techniques in order, to filter and organize our data, incorporating satellite data within our model, then solving partial or differential equations or PDs. That is also fine, looks like it's open, but it's not necessarily as open as it looks. There is so much work which goes in the background. Then forecasting space weather. To show a picture, I try to design a simple flow chart to show how we move through the workflow. For example, we start, then we do the synthetic data, then move to plasma model. Then we interpolate our data, which comes to forecast. Then the web application. My team was more data model, plasma model. And we have another team which deals with the web application or the software, which is also another department or another team. Then another one going to the satellite. We start with the satellite data, taking satellite data, then generate a mesh in space and time. Then integrate satellite data into our plasma model. We could combine this to be able to get the results which we're trying to anticipate. Then we created an equation because we're designing literally our model from scratch to do whatever the results we're trying to get through our model. We create moving clouds. Each cloud has a density profile. So we came up with this equation, which is density, which equals the summation of n equals, all these are different parameters which are going to influence our model when we are working. And just a simple note, this equation is in Cartesian, so it doesn't necessarily mean that our data we're dealing with the Earth is flat. So when we move to our model and develop it more, we are going to change this equation and put it in spherical coordinates because we are dealing with Earth, which we all know it's a sphere, not in Cartesian coordinates. So this is like a trial equation, which we started with in Cartesian doing a XY. Also, all these parameters control the size, speed, and movement. So I try to show each of the parameters in that equation, how they work and how they control or they contribute in our equation. For example, A, which sets the initial amplitude of the plasma density, then V subscript Xi and V subscript Yi, which dictates how quickly the plasma blob moves and time. That is based by our lambda and alpha, and the direction respectively. Additionally, we have the C subscript naught I plus T squared, which affects the plasma density decays over time. So that also shows in our equation as T increases, our denominator is going to decrease, so our value is going to shrink. Then with our equation, we wanted to test it to see, are we able to get a moving cloud? And if we do, how does it respond with respect from different time intervals? So we wrote a code and tried to design in a way and try to run the code and simulate it to see how our cloud moves. So this, the graphs show how the more you increase it, moves from different direction for increases as time moves. So from, for example, X, it moves through X, so it keeps on increasing depending on what. So we're considering the plasma density. The y-axis shows you the plasma density, and the x-axis shows you the x-axis. This is pretty much the same, just showing at different time intervals. Here we started at 2.5. When t is 2.5, then went to 0 to test what we have, then moved on to 5, then we moved on to 10, and show like our cloud is covering up almost the whole space. Then with our data from the code we designed, we decided to use synthetic data from our code to simulate the real space weather environment using satellite data and visualize how that cloud would go on the map to present how our model would be working. And this picture depicts, for example, a map somewhere, for example, in Europe. And this dark place shows you how our cloud will be moving to be able for us to predict space weather in given areas. Lessons learned from this internship, like I say, one which is not written here is how to be discreet, but at the same time be able to explain or express yourself and let other people understand what you're trying to talk about. But for example, my department, we deal so much into plasma. So this was an opportunity for me to understand more about plasma modeling, because I never done it on an industrial point of view or on an industrial scale, which was really a good opportunity for me. Then teamwork and collaboration, like I say, we had like at least 3 groups. Where we have to work together and report to each other through different ways of communicating. You have to write code and collaborate. I was collaborating with Drew so much about the code we are writing, then collaborate with Dr. Spencer about designing the model, coming up with those equations and functions from scratch. So that was really a good opportunity too. Then ionospheric understanding, like I say, most of the time in our department, we deal with the plasma, which is on a way higher altitude. So this was an opportunity for me to learn more about our plasma, but from an ionospheric point of view, which was also a challenging opportunity, which actually has increased my ability to desire to improve my skills. So if an opportunity presents, I was talking to Dr. Spencer, we may be able to collaborate on some projects and continue working together, because I was intrigued on different projects they are working on. And if time permits and opportunity from my school allows, I could definitely continue working with them. Then also understanding space weather through the ionosphere. This was also a great opportunity for me. I've done several projects to do with space weather, but then with my background in engineering, so it was a good chance for me to see how you can collaborate the space weather, the science into like physics, and then adding the engineering, how you add all those skills to help improve the world, and then follow through from the ionospheric point of view. That was a great opportunity. Then high-level programming in Python. Since we're trying to design a new model, so there was a lot of coding and collaborating, learning, using different functions in Python, which I know most of that knowledge will be transformed to do when I'm doing my research in my PhD. So that was also a great opportunity. Also, an introduction to the industry, aerospace industry, and understanding the industry. That was also a great opportunity for me to understand the market, the opportunities, the challenges, how the market is moving, and the opportunities which are there for scientists. Because most of the time, most PhD people wish, like when you finish your PhD, The only place you have to go through is academia. But this was an opportunity to see people who are in academia, but at the same time in the industry, using both their knowledge like to help other generations improve their learning activities, while as well as changing the world through the knowledge they acquired. And that's about it about my presentation. Thank you.
Good afternoon, everyone. So I'm here today presenting my internship project, which was with CFDRC, CFD Research Corporation in Huntsville, Alabama, as a part of the SEPTA internship program. So my project was on multidimensional and multi-species laser plasma simulations with AMR codes. And I was mentored by Dr. Robert Arslanbekov at CFDRC. So the findings and conclusions, just a small disclaimer, the findings and conclusions or recommendations expressed in this presentation does not reflect the views of the NSF or National Science Foundation. These are solely my views and the author's views. So today's presentation, I'll cover these are the table of contents, and I'll cover introduction, my methodology and code structure, the results and discussions, conclusion, and then a few miscellaneous topics like acknowledgement and impact on my internship, on my career. So in this project, I have used Basilisk, which is a commercial software package used for finding solutions of partial differential equations in an adaptive Cartesian mesh. And it was developed by various researchers across the world who have individually contributed to develop various libraries which we use in our simulation code. And these libraries help us to model different physical phenomena. And Basilisk is applied in this project. It is applied for multi-physics modeling as well as a variety of problems related to gas discharge and laser plasma physics in multi-dimensional and multi-species setting. In the next slide, I'm covering the core structure and the methodology that the code uses. So it is based on C programming language, and Basilisk is an extension of the C programming language. In C, we use header files, which contain a predefined standard library functions, which we import during our simulation run. The .h is the extension of a header file in C programming language. And we often use these header files by using a directive called include. Now to carry out simulations, which was generated over nanosecond pulse laser ablation of various materials, we have taken advantage through our model of the Cartesian mesh framework that enables plume simulations out to centimeter distances over tens of microseconds. Additionally, our model and computational technique enables comparison to laser plasma applications where long-term behavior of the plume is of primary interest, such as pulse laser deposition and modification of materials. We introduce experimental constraints within our simulation, such as boiling point, thermal conductivity, density of the target material, ionization potentials, laser pulse wavelength, the pulse duration, and etc. So after running our simulation, I'll show you a demonstration of how the output of the simulation, which is in the form of a animation file, it shows us how the laser plasma or the laser plume behaves within the given constraints. So in the video, I'm showing that through a visualization tool called ParaView, I can select multiple parameters to visualize, such as density, velocity, temperature, pressure, etc. So in this demonstration, I'm using density as a parameter to demonstrate how the laser plume behaves with at different time. Here you can see the time is moving in, the time is in seconds, and it is moving from 0 to the number of time steps we have. Here in the animation, you can see how the plasma evolves during this time period. And also this is demonstrating how the density of the plasma evolves during this time period. And this laser plasma simulation was for copper. Here we can also visualize the same different parameters that give us that we have uh, simulated, such as density, velocity, etc. So in this graph, you can see I have plotted density versus position at time 125,024 nanoseconds and 250,050 nanoseconds. So through the visualization tool, we can visualize at each time step how the density of the plasma bloom behaves, and the peaks resemble uh, the temperature or the peaks in the density when it is red in the simulation animation. Sorry, here it is. So in the previous slide, we used an older version of Basilisk, which was around 4 years older than the newer version. And during this program, I also used a newer version of Basilisk and ran both the simulations parallelly on both the Basilisk. So this is the newer version of Basilisk, and the graphs show the copper's density versus position graph within the laser simulation. The time is around this similar time frame, 125,000 nanoseconds and 250,050 nanoseconds. In the next slide, I'll give a comparison of how these two versions of Basilisk compare against running the same simulations. So you can see there aren't many differences, but they look very similar to each other. On the left-hand side, we have a new Basilisk, the runs on new Basilisk, and on the right-hand side, it is the old Basilisk. Both of them are the graphs for density versus position at two different time frames, around 125,000 nanoseconds. Later, we can also use the visualization tools to graph the linear parameters such as vapor number density, velocity, temperature across the time frame. We do that by introducing a laser probe within the simulation, which captures this information. On the left-hand side, you can see the vapor number density, or NO, versus time is using the new Basilisk, and on the right-hand side, it is the graph shows the same parameters using the old Basilisk. There aren't many differences within these two uh, simulations, and the graphs look similar. Here we have temperature, which also temperature versus time graphs for copper using the laser probes. These are very similar, and it shows that our newer version of the code that we were running for newer Basilisk is able to generate similar results as the older version of the Basilisk. Here it is velocity in the x direction versus time for copper. In the next, we ran simulations for platinum as well, and I'll show you the animation. So here you can see this is velocity, which is evolving in the given time frame, and it starts off the plume starts off very small and then expands into the given space within the simulation. And the space is adaptive. Whenever the plume expands the given area or the volume, the code handles that by expanding the volume uh, of the box or the simulation or the boundary parameters within for which the plume is uh, for which the simulation is running. So whenever the plume expands a certain threshold of the box adapts to it and increases the value of the perimeters. Here we have density versus position graphs for platinum using the same visualization tool, ParaView. And here the time step is around 120,000 nanoseconds and 250,000 nanoseconds. And this was done using the older Basilisk. In the next slide, I have the newer version of Basilisk and to give the graphs for platinum, which is density versus position. In the next slide, I'm comparing these two graphs to showcase that there hasn't been much difference in the results that we get from running the simulation on the new Basilisk, the new version of the Basilisk. So you see on the top, which is 125,000 nanoseconds, the density versus position, we see a similar graph with the old Basilisk. We have two peaks around the same given time frame, just under 300, and at the bottom, when the time step is 250,000 nanoseconds, we have a peak just below 400. Here, it gradually decreases. And also, if we expand the x-axis to zoom into the graph, we'll see a similar result where this slope gradually depreciates. In the next slide, I have the linear graphs, which are time-dependent graphs for platinum using the laser probe, which was capturing the information during the simulation. Here we have vapor number density on the y-axis and time on the x-axis. These two graphs have some discrepancy, but comparing other parameters, it gives us similar results, such as temperature here is quite similar, but there's some discrepancy which I am planning to look into during the extension of this project with Dr. Kamada. And here we have the graph of velocity in the x direction versus time for platinum. So overall, we have carried out a 2D axis symmetric simulation for laser generated plasma to expansion distances pertinent to thin film deposition and materials modification. The simulation implements laser-induced surface evaporation and plasma expansion model. And using our fast computational framework, we can impose various constraints to mimic real-world experimental conditions, which I shared in the during the earlier slides, like the ionization potentials, thermal conductivity, and the other parameters. So our simulation is extendable to plasmas comprising of additional multiple chemical species that may have future impact in the creation of binary, ternary, or quaternary compounds, for which laser synthesis has a definite exploratory advantage over other methods. During this internship, I got a chance to enhance my coding skills and learn a new programming language, C and Basilisk. And this also helped me develop and understand how to utilize plasma simulation models using professional software packages and build solvers to model plasma behavior at high pressure and vacuum conditions. And I also learned what is the differences between working in academia and industry. And I want to thank Dr. Robert Arsenbekoff and Dr. Professor Andrew Kamata for collaborating on this project and guiding me throughout the internship. And this could not be possible without FTPP's program, SIPTA program, and the NSF's funding to enhance competitive research in plasma science. These are the references, and that's all I have. I'm open for questions.